Hello students, today we'll go for the unit 1, okay, of your fourth semester syllabus. Okay, so that is what we are going to learn about the different types of ligands. Okay, different types of ligands, usually which are of the having the pi electrons, which are having the pi electrons. Like in previous semesters, you have used the coordination with the sigma bonds, okay, sigma electrons or sigma bond ligands with the metal. So in this chapter you are going to learn about the pi electrons bonding with the metal here. Okay, so this is what you are going to learn here of the most of the unsaturated organic fragments. Okay, unsaturated type of organic fragments you can going to see to see the bonding between the metal to ligand bond. This type of bonding you are going to learn in this chapter of this fourth semester unit 1 year. Okay, so probably before starting, I hope that you all are very well with your health and taking care of yourself. Nothing to be getting panic. Okay, so just take care and be in home. Wear the mask wherever you go outside. uh, be careful and use some oil, coconut oil, to your hands, okay, like this. And wherever you go you can take the precaution, so nothing to worry about that. So the same what we are discussing here, so what you do, you make notes of these points, okay. So when the real class starts offline, so what happens again, there may not be the time to go for this whatever we are learning now, or to again to repetition of the classes, so there may not be time. So we may not get the time, so that's why what you do, so while I'm discussing here in the video itself, so you can go through and make up points and notes, so that we can complete one by one. And when the offline starts classes, okay, school classroom classes, then we can directly go for, we can skip this unit and we can go for the units which we are not covering here, so that will be very fine. Okay, fine. Now first, the best example for this pi bonded is the alkene. This is what is there here, and they will ask in the examinations. Okay, so this alkene complex is alkene, and alkyne complex is, okay, alkyne. So carbon having triple bond and carbon having the double bond, so like this. So this is what you can see the ligands, the best way to study. And the most important here comes is JC salt. This is always, I think you have learned this in the previous chapter, previous semester also, that is JC salt. Okay, so what is this JC salt? JC salt is nothing but so it was been synthesized in 1827. Okay, so in 1827 by Danish chemist. So this is very much important, by Danish chemist. Okay, so and he prepared it from the salt, that is potassium chloride, okay, KTCl, KCl, and with the potassium chloride, platinum chloride, PTCl2, okay, and in the presence of ethanol, ethanol, okay, C2H5OH. This is what the combination he took, and he had a reaction of this combination, and he got this potassium, okay, so K2PtCl4. So this is what monohydrate. So this is what he treated with the ethanol, okay, C2H5OH, and fortunately, very nicely, he got the complex that is called JC salt, that is potassium, like this. Then you can have this pair here, bond here, and you can see here PtCl3 and C2H4 dot H2O. So this is the called JC salt, okay, monohydrate. This is called water of crystallization, okay, PtCl2 dot C2H4, so ethylene, okay, dot mesh containing coordinated ethylene. So you can have here the coordinated ethylene. This is a coordinated ethylene to the metal here. So platinum is a metal here. So this is what it happens here, and you can see here the water of crystallization, as I said, okay, and the metal is bonded to both the carbon here. So you can see how is the bonding. The metal here PT is bonded to both of the carbon here in this fashion. You can see here. So this is PT, and you can see here this is chlorine, okay, so like this. So this is carbon and this is carbon, and this hydrogen is more like this. You can see here they are having yeah, they are bonded away, far away from the hydrogen, are bonded far away from the minus sign, and from away from the metal here in this way. Okay, so like this, or you can take it like this, H, and you can take here H in this way. Okay, so this is your Cl and this is your Cl. So this is what minus. So this is the complex here like this. Okay, Pt, then Cl is here, so Cl here, then Cl, and this is directly bonded to the pi bonded ethylene here. So carbon is there here, carbon is there. Okay, so alkene is directly it is bonded to the pi bond here, and this substituent hydrogen are a little bit far away from the metal here, somewhat tilted this way. Okay, minus charge. So this is how it has been module here. This is how we can show the complex here. Okay, and the metal is bonded to both of the carbon here, so you can see here the metal here is bonded to both of the carbon here, and and the four, you can see the four CH bonds are bent slightly away. So I said you the CH bond here, they are bent slightly away from the metal. They are bent slightly away from the metal, and this allows what does this allow? This allows the metal to bind efficiently with the to the pi electrons of the alkenes. So here like this. Okay, these are the pi electrons of the alkenes, and it is going to bond very efficiently with the metal, and by which you can see here these substituents, they somewhat differ back to the they bend back bend away from this metal here. Okay, so this is what the mechanism here, and you can see the this is salt. Okay, here this is salt. The best bending picture is given by Dewar chart model. So it is given by Dewar chart model. Okay, this is also very important, Dewar chart model. So this same bonding has been discussed by the Dewar chart model. What he says, to take the metal, so it is having some orbitals in this way. Okay, these are some of, and these are the field orbitals like this. Okay, so these are the field orbitals of the metal like this. Okay, and you can see here, so this is a carbon, and you can see here this is a carbon like this. Okay, and here also I will write here field orbitals in this way like this. Okay, so these are also the field orbitals of the metal here like this. Okay, so this is an empty orbital, these are the field orbitals, and here you can see here the pi star orbitals will be there of carbons. It will overlap in this way, pi star orbital of carbon overlap in this way like this. Okay, so you can show very nicely in the book here like this, and you can see here this is empty and this is a field orbital like this. You can show in this way. Okay, so what happens here, this is a field orbital of the carbons like this, sigma bond. So what will happen here, the field orbital of this alkene carbon pi bond here, so it is going to be donated here like this for the empty orbital sigma bond via sigma bond. I will tell you that, and this is going to form a sigma bond in this way, and simultaneously there is a back donation from this filled metal orbital to the empty pi star orbital. So this is a pi star orbital of the alkene like this, empty pi star orbital of the alkene like this. Okay, so there is back donation this way from filled metal orbital to empty pi star orbital of carbon, and from filled sigma orbital of this carbon, okay, to the sigma or bond of this metal here. So they are going to form the sigma bond. So this is what we can, this type of a model picture is given by this picture is given by the Dewar chart model. So always this will be asked in the examination. Okay, so this is how you have to draw the picture whenever this is been asked here. So this involves as I said, the donation of the carbon-carbon by pi bonds. Okay, so pi bonds electrons to the empty d sigma orbital. So you can see here, so this is an empty d sigma orbital, this is the empty d sigma orbital. Okay, so this what here is there, so this is the empty d sigma orbital, and pi electrons is donated to this empty d sigma orbital of the metal. Okay, and so this electron pair is now delocalized toward the three carbon here. So now this electron is delocalized between the three carbon now here, 1 2 and this metal. Okay, so three centers, so metal to carbon and this carbon C dash you can see. Okay, so and now when this is happening here, so what will happen, this is accompanied by the back donation. So you can see here there is a back donation from the d pi orbitals, as I said, into the ligand here. So d pi, this is a d pi orbitals. Okay, so this back donation will be from the d pi orbitals. So by d pi orbitals from back donation will be there to where, to the LUMO. So these are the LUMO, that is lowest unoccupied molecular orbital of carbon-carbon double bond pi star. We term it as a pi star, carbon-carbon double bond, that is a pi star. Okay, so 11. So this is how this type of carbon, this type of model we call it as a Dewar chart Duncanson model. Okay, so this is similar to type of carbon monoxide bonding, is it right? So in previous semester you have learned the carbon monoxide bonding with the metal. Okay, so this is what it is being, and it is been shown by the sigma bond. Okay, and this is a pi bond, so sigma bond and pi bond. So this is what, and you can see in the carbon monoxide. Okay, so sigma bond, it is insufficient here for the tight binding, so that only metals capable of pack donation. So here what happens, so like D0 for carbon monoxide type of bonding. Okay, so like D0 or like you can see the example you can give for D0 is titanium 4, titanium plus 4. Okay, so they don't bind well for this carbon monoxide. Okay, so because why? Because they don't have any electrons. D0 system, it is titanium plus 4. So that will not be a good binding with the alkenes here. So why? Because there is no electron for the pi back donation. So there is no electron for the pi back donation. So this is what very much important. Okay, so D naught system will not prefer for the binding of the alkenes well here, like in carbon monoxide. Okay, so CO, okay, by sigma bond we are referring, so definitely it's so good, but in alkenes it is not possible here. Why? Because if D electron, there is no electrons, D0 like titanium, so from where there is a back donation. When there is no back donation, then there will be no good binding to the alkenes. So this is contrary, so alkenes will not have the good binding with the D0 system. So this is what you have to keep in the mind. Okay, so this is one part of the talk of this unit 1 here, that is the mode of binding here. And you can see so these two diagrams you have to keep in the, like previous I had shown you. One is the simple salt of JC salt, another one is the Dewar chart mechanism of the binding. Okay, now during this binding you can see that the carbon carbon double bond. Okay, so this is what here bond of the alkene is lengthening on the binding. So the CC bond is lengthened here, so double bond, if whatever is there, so the CC bond, if you see the bond length, so it is lengthened during the binding here. Okay, the metal alkene sigma bond, why, what's the reason here? Because here metal is there and here alkene sigma bond is going to form. Alkene sigma bond, it depletes the pi electrons. So what happens here, pi electrons is there, no, it will be donated by this alkene here to the metal, so it depletes the pi electron here. Okay, during binding. So when the electrons are depleted from here, so what will happen, normally this bond length will be increased. Okay, because the partial transfer of electrons to the metal is happening here, and that slightly weakens the length here, the weakens the bond here, carbon carbon bond, and therefore it lengthens it. This is what the main important reason you have to explain. So why this bond length is increased. Okay, upon binding with the metal. So that is what that is a partial donation of the electrons from this, and that's what it weakens the carbon carbon bond here, and it lengthens it. This is what okay, and the major factor in lengthening the C double bond carbon carbon bond here. Okay, so however what happens, it strengthens the back donation. So when this happens, what will happen, it strengthens the back donation. This case of lengthening of the bond length here of carbon carbon by draining the electrons from here, simultaneously it increases the back donation also from here to the carbon pi star orbital. So this is going to facilitate this bond. Okay, so this is very much important, back donation. And sharply you can see there is a lower, the carbon bond order is lowered here, carbon carbon bond order upon coordination to the alkenes. Okay, so if you see for weakly pi basic metals, so for you, if you take the example of weakly pi basic metals. Okay, if you take this for the weakly pi basic metals, okay, this you can see the reduction is slight, but for a good pi base, if you take the reduction is less here. So if you take a weakly pi here, so reduction of carbon carbon bond length is less here. Okay, so this is what a weak pi base means, there is no electron. That means what back donation is less here. So if you go for the weak pi base ligands, okay, back donation is less, so obviously this carbon carbon length also is less. Okay, so there is no lengthening is more here. But if you take a very strong pi basic, if you take a very strong pi basic metals, that means what, now this metal is very ready to give the electrons via back donation. So what will happen now? So obviously you can see this carbon-carbon bond length also becomes more, length becomes high, becomes large, or it weakens more. This carbon-carbon bond weakens more and the bond length becomes high. So that's why so for a good pi base, the reduction is almost to the single bond. So what happens here, the carbon-carbon what double bond we are showing here, if it is a very good pi base metal, if we take, so definitely it comes to the single bond, that much it reduces. Okay, the bond length it reduces. For example, if it is 1.38 Armstrong, it goes to 1.43 Armstrong, that much it is increased here. So from double bond to single bond, this is what just I have given you, but the increase is more here if you are going to go for the good pi basic metal. That means metal should be rich in the electrons, so that is good for this type of mechanism. Okay, and if you see that for JC salt itself, it is having the metal JC salt, it is having the metal to ligand sigma bond. Okay, sigma bonding. So this will predominate because of platinum 2. So this is very much in JC salt. Okay, this is metal to ligand is predominating here, ligands, because of the platinum 2 is a weak pi base. So platinum 2 is a weak pi base. See, JC salt is having the weak pi base. So this is very much important. Okay, so platinum 2, what we are seeing in the JC salt is a weak pi base. Okay, so because of this, what will happen here? The sigma bond predominates here. So sigma bond is in this JC salt. The sigma bond is predominating. Sigma bond is predominating. Yeah, okay, because platinum 2 is a weak pi basic. So sigma bond is predominating in the JC salt here. And you can see here the carbon-carbon bond, what it is, if you see the carbon-carbon bond length, which is 1.3, I think 37 Armstrong. Okay, so 1.37 Armstrong, just see, if I remember this monthly, I think the 1.37 Armstrong initially resemble 1.37. Okay, so if you see for the free alkene, I will write here, if you see the free alkene, it is 1.337, I think Armstrong. Yeah, if I remember, 1.337 free alkene, 1.337 Armstrong, but when it coordinates with the metal, it becomes 1.37. Okay, 1.37 from 1.33 to 1.37, not much large difference you can see here from 1.33 to 1.37 here. Why? Because platinum 2 is a weak base. Okay, so there is no much back donation from the metal to here, and that's why there is no much increase in the bond length of carbon-carbon also. Okay, this is what you have to remember. So here what happens now, one thing, free alkene, you are having the carbon-carbon bond length is 1.33 Armstrong, 1.33, but when it binds it becomes 1.37 Armstrong. So not much difference is there. Why? Because platinum 2 is a weak base, so back bonding is less. Means what happens? So bond lengthening will be less here of carbon-carbon, so weakness will be less here. So this is what is the importance here. Now if you see here, it depends on the substituents. So if I go for this one, so it depends on the substituents. Okay, so carbon alkenes is there, so this substitute depends on the substituents of these alkenes here. Okay, so what does this mean? What does this mean here is if the substituents, how they bend, they can bend away from the metal, or they can be close to the metal. So this depends on the substituents what we are using here. Okay, they only slightly bent back, usually back away from the metal, and the carbon-carbon distance is not greatly lengthened here compared to the free ethylene. Okay, in contrast, if you take platinum 0, okay, in platinum 0, if you take this in contrast, it's much more strongly pi basic. Now what happens, platinum 0 is a much strong pi basic. Okay, and if you see this compound PT, P triphenyl phosphine twice C2H4. Okay, if you see this compound, platinum triphenyl phosphine C2H4 ethylene. Okay, if you see this compound PT PPH3 twice PT PPH3 twice triphenyl phosphine, okay, by di C2H4, okay, ethylene, the carbon-carbon distance becomes much longer in this case. So the carbon-carbon becomes 1.43 Armstrongs here in this complex here. So carbon-carbon distance is 1.43 Armstrong. Which one? Platinum 0, that is PT PPH3 twice C2H4. Okay, PT PPH3 twice C2H4, the carbon distance is much longer. Okay, in such cases you can see the metal-alkene system approaches almost to cycloropropane. In this case what happens, when the carbon-carbon bond length is too high, because in this complex platinum is in zero state. When platinum is in zero state, there is very good back donation. When very good back donation is there, so definitely you can see the carbon carbon in ethylene C2H4 bond length will increase. So this bond will be in lengthened now. So how much? So 1.43 Armstrong, can see here. Okay, in JC salt it is 1.37, but in here in this complex it is 1.43, too much large. Okay, and 1.43 Armstrong means what? In this case, the system approaches now. This system, very new word is there here. The approach to metallocyclopropane. So we write it as a metallocyclopropane. Metallocyclopropane. So this was a metallocyclopropane system. Okay, this is what. So it extreme case. So this is what. Whenever there is very good donation of the electron from the metal, so it is going to approach the metallocyclopropane model. Okay, the extreme case we say it here. Okay, so in this it is just like in this way. So I will write here. So this is like this, like this, like this, like this. So you can take it here, hydrogen, hydrogen. Here also any substituent, I am mentioning hydrogen here, but any substituent you can it is metal. So this way. Okay, so this is called as a metallocyclopropane. So this figure, this is called as a metallocyclopropane, and this happens when the distance carbon carbon is more, and when metal is in mostly more, means zero oxidation state. Okay, that means good pi basic metals, pi basic good pi basic metal. So this metallocyclopropane model is going to be seen as in contrast with the Dewar chart metal. So if you see, this is a metallocyclopropane extreme, we said. Okay, so when the metal is good to back donate, but in some cases you can see Dewar chart model. So that is what Dewar chart model, you can see like what we have shown in the previous, like this. Okay, so small difference is there here, like this, and here hydrogen and hydrogen, and here it is metal in this way. Okay, so directly sigma bond like this donated. Okay, so this model is called Dewar chart model. Directly you can see here from double bond it is going to see it is going to donate. So here sigma bond is predominant, so here sigma bond is predominating here. Okay, so this is called Dewar chart model. So this is called Dewar chart model, and this is called metallocyclopropane extreme model. That is what, when the metal is very good enough to donate the electrons via back bonding. So this is what about the two model, definitely asked in the or you have to keep in the mind here. Okay, so this two model is very much important. So this Dewar chart model involves minimal pi back donation. So this is a very minimal, MINIMAL, minimum, less pi back donation. Okay, minimal back donation. So this is what involved. But the two models, both models involves NITA2, that is bidentate ligands. Okay, NITA2 structures. So both models you can see they are involving the NITA2 models here. Okay, so this is how about the and one thing you have to keep in the mind here in these two models, that if the presence of electron withdrawing group, so EWG I will write here, electron withdrawing group, if any substituent is present of electron withdrawing group here, okay, in this model, so what will happen if this substituents are groups are on the alkenes, what happen? It encourages the back donation. So electron withdrawing group, what will happen? It will encourage the back donation. So I will write here, very important point. So it will encourage, okay, it will encourage the back donation. If there is electron withdrawing group, it will encourage the back donation. This is very much important. Okay, back donation, and it makes the alkenes bind more strongly to the metal. So back donation when increases, what does it make? It makes the alkenes now to bind very strongly. It makes the alkenes to bind very strongly with the metals. Okay, so because of the very back donation, very strong back donation, so there is a very strong, makes alkenes bind more strongly to the metal. Okay, this is what very important point to be noted. For example, if I take to clarify this, for example, if we take as PT, okay, platinum PH3 triphenyl phosphine twice C2CN4. Okay, this is what. So instead of hydrogen, I am taking the very strong ligand here, that is very electron withdrawing cyanide, CN 4 times. Okay, C2C4. That means CC like this, and I am having CN. I am having CN. I am having here CN, I am having here CN like this. The substituent is very much electron withdrawing group now. Okay, cyanide is there here, and this is alkenes, and here it is metal. Now binding is there here in this way. Okay, so what happens here now? So has even larger now. Here the distance is more longer now. The carbon carbon distance 1.49 Armstrong now. You see 1.49 angstrom, still longer now. Why? Because I have attached what now here, electron withdrawing group. So carbon carbon bond distance becomes still longer now, because it becomes very weaker. Why? Because this becomes very strong electron donating now. Okay, because this becomes very strong now. What? Back donation. So this facilitates the electron negative group substituents, which facilitated the very good back donation here. And by this result, what happens here, the carbon carbon bond length distance will again increase 1.49 angstrom. And if you see, then the normal, what's normal CC bond, what is 1.33 angstrom. Okay, so normal carbon carbon distance in ethylene is 1.33, but it increases 1.47 when it binds to the more stronger electron withdrawing group here. Okay, so similarly, in Dewar chart model, so like this in Dewar chart I have said here. So in this model, okay, in Dewar chart madam, ligands, they are very weak here, so such as triphenyl phosphine ligands. Okay, such ligands can be used in Dewar chart, which is a weak, not a electron very strong ligands here, but inside metallocyclopropane extreme, we can say that in such cases you can see the very strong ligands is been used, and that will like cyanide and all, and that will lead to which type of model? That will lead to the type of what you say, metallocyclopropane type of model. So this is how in a brief in today's I think class, this is more sufficient I think in today's first class here to know the major bonding of the alkanes. Okay, bonding of the alkanes to the metals. Okay, so via pi bonding. So this is what the bonding of pi electrons. Okay, so this is what we are learning today, and I think this is in today's this one, you make these notes. Okay, draw the structure very nicely, this pore structure, and show this Dewar chart model very nicely. Okay, so this will be asked in the examination. Okay, and give the structure here, Dewar chart model. So this is how, okay, how it binds, so how the back donation takes place, sigma bond, everything. Okay, and finally you can show these two models, that is what I had explained here, two models of metallocyclopropane and the Dewar chart model. Okay, so these two models, some examples so of the electron withdrawing group, what it happens, and so this is what. Okay, in the next video we will learn some spectroscopy, okay, of this bonding. Okay, what happens in the NMR IR. Okay, carbon NMR or proton NMR IR. So what happens, some IR we learned it here with respect to the bond 1.43. So this is what, so NMR we will touch over in the next class, and we will learn something more on these alkenes, and followed by the next we will go for, that is alkynes, if it is carbon triple bond bindings. Okay, hope you understood this first this one, and I will upload this in YouTube also, so whenever there is time and good network, so you can follow this video. And Monday in the Zoom we will discuss this. Okay, so nothing to worry. So online in Zoom, so you go through this video and learn more, and if any doubts you are having this, we will have a discussion in the Zoom meeting. Okay, so this is what we can do it with respect to the timetable, whatever is given. So Monday I think 9:30 will start with the first class. So all of you join the Zoom meeting. So before that you work on to this video, okay, and make a points on this video, and we will have the discussion on the Monday on particularly on this concept. Thank you.